Hi y'all, this is Mrs. Quigley, the coolest and most broken of all of the math teachers. This is the first video I've done, and I'm still turkey stuffed, so I can't guarantee how amazing it will be, but hopefully it'll get the point across. In this section, we're going to be talking about scatter plots and lines of best fit, which should be vaguely familiar to you guys. I know I covered them when I taught 8th grade 2 years ago, so this shouldn't be anything terribly new. You'll see that you have a worksheet that is guided notes, and on top of that, I have blown up a few of the examples that you will see will match up perfectly to the examples on the worksheet. They're just easier to see. For example, if we took this data given a sample of married couples, you would see that you can track as the husband's age changes. Generally, there's a pattern that as the husband's age goes up, the wife's age goes up. You'll notice that there are a few kind of outliers here and there that you can see. This particular dot right here, this would mean the husband's age was around 53 and he married a gal that's almost 10 years older than him. So this guy knocked it out of the park, married an older woman. And then maybe this one down over here. This one, there was a gentleman that was 70 married to a maybe 57-year-old. And he must be quite a man to have married a girl almost 15 years younger than himself. Anyway, that's a general idea of how we would read this chart and the data on it. As you look at the pattern, you can see something specific happens, and this is very useful to people who are looking for patterns that will be predicting future behavior. You'll see this comes up a ton in almost every kind of business you can think of. So if you're looking for something where this is actually applicable to your future, this is one lesson that will be. If you look at the next example here, you can see that these are the ages of American women when they get married for the first time. And you can see it's tracked by date and by age. Date on our x-axis and age on our y-axis. And again, as we plot these points, they aren't so grouped as in our last example, but there's a clear and distinct pattern here. We're going to learn the vocab that communicates these ideas about sharing what this data means and use it to predict future behavior. Again, in your last example right here where it says smoothies, in my example, you can see that again, there's a pretty clear behavior that depending on how many grams of sugar there are in your smoothies, that the calorie content of each smoothie tends to go up. That makes sense. The more sugar it is, the better it tastes, and unfortunately, the more calories it has. If I was to look at this group of data right here and want to be able to make a general line that would fit through this, I can kind of eyeball it. And as you get into more advanced math, there are extremely in-depth calculations that go into creating this line. But for now, we are just going to find a line that incorporates as many of our data points as possible. If I was to do that, and I want it to be a fair representation of both the points above and below my line, I would probably make it look something like this. Now you can see there's a few more below, but then there is one point that's quite a bit farther above. So for me, I felt like this line would pretty clearly reflect the data that's given to me in this graph. That brings us to our vocabulary. If you look at your first word there, a scatter plot is, and this is where you need to be writing in your notes, I will read this slowly. A scatter plot is a graph that shows a relation between two data sets. One more time. A scatter plot is a graph that shows the relationship between two data sets. That one is pretty clear. Now, a word that you'll use commonly or hear commonly when looking at scatter plots is the word correlation. A correlation is a relationship between those data sets. One more time, a correlation is a relationship between data sets. And there are three kinds of correlations that we'll talk about in this lesson. That is a positive correlation, a negative correlation, and no correlation. But we have an example of that if you look left. When you're talking about correlation, what you're really looking for is the slope of the line. If you look in our first example right here, if we were to put a line of best fit or a line that most accurately represents that data, you would see that that line would go, if we're going from left to right, it would be moving in an upward direction, meaning as x increases, y increases as well. If we look at our next graph, you'll see that if we were to draw a line here, this line would have a negative slope or be going in a negative direction as we go from left to right. That means as x increases, y decreases. In our last example, there is no rhyme or reason to this. It looks like my score sheet after playing a game of darts, and I am not good at darts. There is no correlation to these points whatsoever. They appear to be random, and there is not a pattern. So of these, the first one would be a positive correlation. The second would be a negative, and pardon my handwriting, my broken wrist is healing, but it's not perfect. And then the last one, we would have no correlation. We can also look at data points and be able to determine if there is a positive, negative, or no correlation. So my blown up set of those tables in your notes looks like this. We can see that if we were to look at these, one way you could do this is to plot your data. Another one is to look at your pattern going from your smallest numbers to your larger. If you look at the bottom example, you can see pretty easily that as x increases, y decreases. And when that happens, that fits our definition of a negative correlation. When you look at the first example, we can see that our smallest number is 71. From there, we're going to go up to 75. Oh, sorry, our smallest one is 68. And you can see that in the down here, it's counting a number of attendees, and there's 1.7 thousand. As we get up to 71, there's 2.9 thousand. From there, we go up to 75, where there is 3.8 thousand. 78, where there is 4,000, and you can see that as my x increases, my y increases as well, which means there is going to be a positive correlation. Now going back to your note sheet, I'm going to give you an example problem. Given the data below, and here's a graph, tell whether there is a positive, negative, or no correlation and give the equation of the line of best fit. I've gone ahead and given you the graph of that data, but often you will have to graph that yourself. So our step one here is that you are going to make a graph of the data. Our graph is modeled over here. Our second step is going to be decide if the data can be modeled by a correlation. It's like correlation with 2 R's. If so, is there a positive or a negative correlation? Well, as we look at this line, as x increases, y decreases. So yes, there seems to be a correlation, and in this case, there is a positive. Sorry, I should have had you circle that instead of drawing a blank. There's a positive correlation, and there's not a negative one. Step 3, we are going to draw a line of best fit. And if you look on the left, I've gone ahead and done that already. Now here's the hardest part. Write an equation using 2 points on the, I'm going to abbreviate, line of best fit. And you can ask your teacher if she prefers you to write that out or not. Now to write the equation of this line, the first thing I need are 2 points that seem to fall pretty clearly on the line. If I look at this graph, I have 2 that fall nice and neat within my grid, so I can tell exactly what those coordinates are. I've got 1 point at 5, 10, and another point at 6, 8. And we know from our previous sections that I can find the slope of these lines, and then I can write the line given the slope. From here, I can find the slope by using my slope formula of m equals y2 minus y1 over x2 minus x1. When I label these x1, y1, x2, y2, I can plug them into my formula here. So I've got 8 minus 10 over 6 minus 5. When I subtract across the top, I get -2, and when I subtract across the bottom, I get 1. So my slope is -2, which works well to support my, oh gosh, up here, I just realized that is supposed to be a negative correlation. I apologize, I said one thing and circled the other. So a negative correlation, and as you'll see, that matches up with my negative, there we go, my negative slope. From here, I can start to substitute that into my formula for an equation in slope-intercept form. Y equals mx plus b. I know that my m, my slope, is going to be -2. Now I'm going to choose my first point here. I should be able to choose either point to make this work, but I'm going to substitute those numbers in for x and for y in my equation here. So I'm going to put in 10 in the place of y, -2 is my slope, and 5 is my x. I do not, however, have a y-intercept. Now, if you look at your graph up here, you can see what your y-intercept is in this case. So let's see if we can make our math match. Here, if I multiply, I'm going to get -10 plus b. Solving for b, I'm going to add 10 to both sides, and I get 20 equals b, which matches up perfectly with my graph. When I substitute b and m into my formula right here, I get that my equation is y equals negative 2x plus 20. Now I could use this formula to predict other points on my graph or even future points on my graph for data that we haven't even been able to collect yet. So you can see how to people in economics or advertising, which are both big money, how this can come in handy in predicting future behavior. That's it, and I hope you all had a happy Thanksgiving.